That was my laptop falling. Unfortunate. Okay, in this video we're going to look at two topics which are both related to the domain of a function, so the set of possible x values of the function. First, we'll talk about what it means for a function to be discontinuous, and we'll discuss the different ways that a function could be discontinuous. We'll think about that both algebraically as well as graphically. And then we're going to talk about end behavior, which really just means what happens as x gets super, super big in either the positive or negative direction. So as x gets closer and closer to positive or negative infinity, what are the y values doing? Are they also going to plus or minus infinity? Are they getting closer to a particular value, maybe a horizontal asymptote, etc.? So first, continuity. We say that a function is continuous if we can draw it without picking up our pen or pencil or whatever off the paper. So that's a continuous little curvy thing that I just drew. This is not, because there's a gap there, right? This is also not if we had something like that, maybe with a vertical asymptote. So there's lots of ways for a function to be discontinuous, but we are only going to worry about two of them. The first one is called an infinite discontinuity. It is also sometimes called an essential discontinuity. All right, these mean the exact same thing. The second also has two names, a removable discontinuity or a point discontinuity. There are other types out there. We don't care about them. I'll show you some examples at the end, but we are absolutely not studying them in this course. So we've just got two types, and each of them has two names. I don't care what name you choose to call them. I just want you to be able to recognize the names when you see them and know what they mean. Okay, so what do they mean? Well, graphically, the removable or point discontinuity means that in our graph, we've got a single point which is missing, and it'll be indicated in a picture like that. So there'll be like a circle that's not filled in. That's where we get the name point discontinuity from, because it's just a single point that is missing. The infinite or essential discontinuity is one that has a vertical asymptote, whatever that might look like in the graph, and that's, I think, why we call it an infinite discontinuity. Don't worry about where the names removable or essential came from. Not important. But graphically, this is why I prefer the terms point and infinite. And so I would recommend that you use those. I think those are easier to wrap your heads around. So if I had a graph of a function, looks something like this, and I were to ask, what are the discontinuous points and what kind of discontinuities are they? We'd look at it and then we'd figure out like, okay, what's the x value of that that missing point there, and whatever. My axes aren't labeled. Let's say that's at -1. Okay, then we'd say there's a point discontinuity at x equals -1, and maybe this dotted line is over here at say 4, so we'd say there's an infinite discontinuity at x equals 4. It should be pretty easy to identify from looking at a picture where the discontinuities are and what type they are. The reason that I've drawn this one freehand is that when we use our calculators or go to a website like Desmos, it's a little bit harder to identify where the discontinuities are because they're not going to label the vertical lines, so you'll have to like use your eyes there, and the removable discontinuities will not show up at all unless you are really, really careful about looking for them. So here's an example of a function that has both an infinite discontinuity and a removable discontinuity. The infinite one you can kind of see, okay, it's going to happen somewhere around here, although it's not super obvious from the picture where it is. It ends up being at x equals 1. And the removable discontinuity you absolutely don't see because it looks like it's filled in everywhere. However, if I were to click and drag along this graph, actually right here at -2, this function doesn't exist. So this has a removable discontinuity at -2, but you wouldn't know that unless you knew what to look for. And I know I haven't even shown you how to identify where these points are. That's okay, that's the algebra. We're going to look at that in a sec. Right now I'm just showing you the shortcomings of using the technology to generate pictures. So here's the exact same graph done on the calculator. Again, yeah, all right, it looks like it's around here, but it's not exactly obvious where it is. And it sort of looks like it's filled in here. The only way to tell that there's a point missing at -2, well, actually, we can spot both of them this way, is to go to Menu and then open up a table. And then we see that at 1, we get the y values undefined. And then also, if we scroll up to -2, we get undefined again. So this table tells you where the discontinuities are occurring, although it doesn't tell you what kind they are. You'd have to look back at the graph and then be able to say, oh, well, at -2, clearly there's no asymptote, so that's a point discontinuity. And at 1, that's definitely an asymptote. Of course, the problem with the table is what happens if the discontinuity is actually at -2.1? Well, then this table wouldn't have spotted it. So unfortunately, if the graph is drawn well, then it's really easy to tell where the discontinuities are. However, if you're supposed to be making the graph yourself, that can be trouble. Thankfully, the algebra isn't that hard. So here's the trick. It's all about dividing by 0. We've talked about that a few times recently. We know we're not allowed to divide by 0. So if we see in our function expression that we're dividing by a 0, that's going to give us an infinite discontinuity. If we're dividing by 0, but that factor cancels out with something in the numerator, we're going to have a point discontinuity. So if I had this expression here, that's going to be an infinite discontinuity. Where? Well, where would my denominator give me 0? Well, that would be if x is equal to -1. Here, I could factor this numerator to get this, and then I see, oh, you know what? That x plus 1 cancels with that one in the numerator. So I'm still going to have a discontinuity at x equals -1, but this time it will be a point discontinuity instead of an infinite discontinuity. So it's all just about factoring and canceling. If you can cancel, then it's a point discontinuity. If you can't cancel, then it's an infinite discontinuity. Here's the graph of 1 over x. Clearly, we can't divide by 0, so we should have a discontinuity at x equals 0. And that's going to be an infinite discontinuity. We have a vertical asymptote. Let's change it to x plus 1 in the denominator. Think about function transformations. How is this graph going to change? It's going to move 1 unit to the left. Now, that vertical asymptote used to be at 0, but it's moved 1 unit to the left. Our infinite discontinuity is now at x equals -1. Here's the second example we saw on the previous screen. It looks like a line. Even though this is a pretty complicated function, the graph looks like a line. Why does it look like a line? Because when we cancel this x plus 1 and this x plus 1, what's left over? X minus 1, and that's a line. Slope of 1, y-intercept -1, that's exactly what we see here. However, if we look really, really closely at x equals -1, we see on the graph that it is not defined. So it has a point discontinuity at -1. This third function is the one that we were looking at a few minutes ago. So it has the vertical asymptote at x equals 1 because this factor in the denominator is not getting canceled out, but it has a point discontinuity at x equals -2 because this factor is canceling with this one from the numerator. Last thing on this topic, we did have other things that we considered when we were thinking about the domains of functions. It wasn't just about being careful for dividing by 0. We also had to worry about having square roots of negatives and stuff like that. So this particular function, h of x, has a domain of x greater than 0. Couldn't be equal to 0 because then we'd be dividing by 0, and it can't be less than 0 because then we would be taking the square root of a negative. So is there a discontinuity on this one? I would say no. I would say that this function is continuous on the domain for which it exists. As long as we're talking about x values that are greater than 0, this function is continuous. And you can see when you graph it that every place where this function exists, you can draw the entire thing without ever picking up your pen or pencil. Don't worry, there's not going to be any trick questions or anything like that. Really, the order that you would consider something like this is you'd say first, what is the domain? Okay, x greater than 0. Second, can I draw all of that without ever picking up my pen? Yes. As opposed to the function 1 over x, which has a domain of every x value except for 0. Can I draw all of those without picking up my pen? No, because I need to skip over the 0 somehow. Okay, so now we're going to switch gears here and we're going to discuss end behavior. And it's called end behavior because we're interested in what's happening at either end of the function, meaning like the left end or the right end. So we're going to look at the graph, or we're going to think about what the graph might look like if we have the equation. And we're going to consider when x gets super, super big in the positive direction, or when x gets super, super big in the negative direction. Side comment, I prefer saying big in the negative direction rather than saying when x gets small, because to me, a small x means it's close to 0. But anyway, as x goes out towards positive infinity, so that's all the way out to the right, or towards negative infinity, all the way out to the left, what happens to the y values? There's basically only 3 different things that could happen here. The first one is that the y value could also be heading up towards infinity or down towards negative infinity. The second is that the y value could settle in on a particular value, some real number, and that's going to be a horizontal asymptote. And for this video, this is all that we're going to consider, is just these 2. There are other options out there. So we have periodic, which just means something that repeats, and we will look at those later on when we do trigonometric functions later on in this course. Then we'll see some periodic behavior, but we won't really discuss that today. So just like before, I want to start off with graphs. They're a little bit easier to wrap our heads around, and they'll give us a sense of what's going on for when we approach the algebra. So in this first example, we have a line. Now as x moves towards the right, so as x goes towards positive infinity, what's happening to the y values? Well, they're going up, aren't they? And they keep going up. There's never any end in sight, so the y values are also headed towards positive infinity. As we go out towards the left, as x approaches negative infinity, what's happening to the y values? Well, they're going down, down, down. So the y values also go to negative infinity. And it's as simple as that. In the second example, down below, we have a parabola. In this case, whether x is going towards the left or towards the right, the y values are getting higher in both cases. So as x goes to positive or negative infinity, y is going to go towards infinity. And on the right, we have just another example that's not a line of something that's going towards positive infinity out to the right and negative infinity out to the left. And of course, in any of these cases, had we considered, instead of the graph of f of x, the graph of negative f of x, these graphs would have flipped over, and then the behavior of y would have changed. So in that last example, had we flipped that graph over, we would have had something like this, and then we would have had negative infinity and positive infinity. Notice that in all these cases, we are never writing x equals infinity or y equals infinity because infinity is not a number, so x and y cannot be equal to it. Here are some examples with asymptotes. In this example up top, it seems that as x approaches infinity or negative infinity, the y value is approaching, in both cases, 2. In the example below, again, as x goes to positive or negative infinity, the y value is approaching 0. I need to point out that a lot of people think that an asymptote is a value that the function is never equal to, but we see in the top example that this function actually is or does have a y value that's equal to 2. So it's possible for the function to cross over the asymptote. What it means to be an asymptote is just that as we go out towards infinity or negative infinity, that then the function gets closer and closer and closer to that value. In fact, it's even possible to have a really strange function that crosses over its asymptote infinitely many times, but still always gets closer and closer and closer to it as x gets larger. But we're not going to talk about these functions in our course, so don't worry about that. Okay, the graph can have more than one asymptote. As we see in this example, as x approaches infinity, the y value appears to be approaching 1. And as x approaches negative infinity, the y value appears to be approaching negative 3. And it could also have an asymptote on one side and not on the other. So here, as x approaches infinity, the function's going up. So the y value is approaching infinity. But as x approaches negative infinity, the y value appears to be approaching 0. Now I'm being pretty careful in all these examples to say the y value appears to be approaching 0, the y value appears to be approaching 1 or negative 3, etc., because it can be hard to tell exactly from a graph. So I promise you, if you're given a picture to look at, it's not a trick. You know, the answer's not going to be, oh, the asymptote was negative 2.9, you idiot, you thought it was negative 3. Like, no, it's not going to be like that. Okay, it's going to be obvious. Where we can tell for sure, however, what an asymptote is from the algebra. So this is when we just have the equation. We don't need to see the graph at all. So for starters, I want to point out that you can kind of just think about it sometimes. For example, if I had a graph of like y equals x squared, well, even if I don't know what a graph of y equals x squared looks like, and look, that's a really easy graph to picture, but even if you have no idea what it looks like, that's fine. What happens when you put a really, really big x value into that equation? Well, then you're going to have a really, really big value that gets squared. What does that give you out? Well, just another really, really big number. What happens when we put in a really, really big negative number? Well, again, we square it, which is going to give us a really, really big positive number. What about this one? If x becomes a really, really big positive number, then I'm dividing 1 by a really, really large number. What's that quotient going to be? It's going to be really, really small. So this one is going to have a horizontal asymptote at y equals 0. And likewise, when I put in x equals or as x approaches negative infinity, I almost said something mathematically incorrect there. Thank goodness I stopped myself. As x approaches negative infinity, then I have, again, 1 divided by a really, really large negative number. Y is going to approach 0. It's going to still be like a negative value, but it's going to be really, really close to 0. Once we know that, once we can consider a really simple function like 1 over x, we can then use function transformations as a shortcut. So for example, if I had the graph 1 over x plus 1, well, I can go through the same thought process as before and, put in a big x value and think about what happens. Or I could just think, well, how is this changed from the previous graph? Well, it's just moved 1 unit to the left. And since it's just moving left to right, that horizontal asymptote, it's just moving a horizontal line left to right. It's not going to change it at all. What if we considered something a little more complicated? Well, now, again, how is that changed from the original? Well, it's been moved up 2 units. So that means that the horizontal asymptote is also going to be moved up 2 units. Sounds simple enough so far? I hope so. How about this one? Well, how does this function compare to the original 1 over x? It seems like it's got a vertical stretch, but that vertical stretch is going to leave the asymptote still at 0. It seems like it's got a horizontal compression and a horizontal shift happening, but that's not going to change the horizontal asymptote at all. It's shifting down by 5. So that's the asymptote. But what if we can't rely on function transformations? Here's an example we saw a moment ago. I could rewrite this function by combining the two terms into a single fraction like this. So all I've done is rewritten it algebraically. The two expressions that are in the green boxes are exactly the same. Their graphs will be identical. But if I look at this one over here, that doesn't shout at me, oh, you know, it's just the original one, but moved up 2 units. So we need to think about this in a new way. The answer is not to try to rewrite it in this form so that you can see the plus 2 again. This particular example is actually not that hard, and you'll learn how to do this in future courses. However, a lot of the functions that we're going to see, this will not be possible for. So we're going to have another way to approach this. Luckily, it's actually pretty easy what to do. Before I show you the trick, I want us to just think again in this form, what's going to happen when we get a super, super big value for x in there? So the numerator, we're going to have, let me just write this out as 2 times infinity plus 3. Even though x is not actually equal to infinity, it helps me anyway to write it out like this. So we've got 2 times infinity plus 3. Tell me, does this plus 3 have any effect on 2 times infinity? I mean, 2 times infinity is so, so big that adding 3, really, we can just ignore that. It has very little effect on the overall value here. And the same thing in the denominator. Infinity plus 1, we don't need that 1 anymore. So now you look at it, and basically what we have here is 2 infinity divided by 1 infinity. And it feels like those infinities should cancel. And if we cancel them out, we get 2, the horizontal asymptote. Now, if I'm being honest, that was a little loosey-goosey. But that's actually exactly how I want us to approach these. So we're going to look at 4 more examples now, and they'll lead us towards a nice little shortcut. And then we'll be able to analyze any fraction with polynomial numerator and denominators. So here's our 4 examples we're going to look at. In this first one, top left, again, we're going to consider what happens when x is a super, super, super big number. Do I really care about this plus 9? No, because I've got super big numbers happening. And same thing with the minus 4 down there. And actually, up here I've got 3 times x to the 4th. Now this is a super large number raised to the 4th power. That's a super large number times itself 4 times. The fact that I'm subtracting 7 of those really, really big numbers really doesn't affect this value at all. This is just so much larger than this term that I can actually ignore that. And what we're left over with is 3x to the 4th divided by 7x to the 4th. And you know what? Those x to the 4ths can cancel, leaving us with 3 over 7. And actually, that's going to be our horizontal asymptote for both of these, because whether I put in a really big positive number or a big negative number, they're both going to end up being canceled in the end anyhow. Now let's look at the bottom left. Same idea. I really don't care about this 9. I really don't care about this negative 7x. I really don't care about this negative 4. Because when x is a super, super big number, positive or negative, these first terms are going to be so much larger than the other ones next to them that I might as well just ignore them. And now, if we simplify this expression, well, rules of exponents would tell us that we need to cancel out the x cubed from the numerator. and just leave us with 1x in the denominator. And now, when I have a really, really, really big x value, I am dividing 3 by a gigantic number. What is my answer? It's essentially 0. And that's going to be true whether x is positive or negative. Now we go to the top right. Hopefully you're catching on here. I really don't care about any of these terms. I just want to look at the largest exponent in the numerator and denominator and then simplify from there. In this case, that's going to simplify to 3 over 7, but I'm going to have x to the 5th up top. Now as x becomes a super, super big number, what happens to the y value? Well, I've got a super gigantic number divided by 7. That's just going to leave me with a super gigantic number. What about when x goes to negative infinity? Well, I've got a super gigantic negative number being raised to the 5th power. That's still going to be a super gigantic negative number. In the last example, bottom right, don't care about any of those things. When I simplify now, I'm going to have 3 over 7, but it's going to leave me with x to the 4th. As x goes to infinity, y will still go to infinity. But as x goes to negative infinity, now I have a negative number being raised to the 4th power, which is going to be positive. So in this case, it'll be positive infinity twice. So what do these all have in common? We're ignoring all of the terms in the numerator except for the term with the largest exponent on the x, and same thing in the denominator. Because all those other terms, when we're talking about infinity, those other terms are all really, really small. And then we're going to simplify it, and we're going to see what's left over. We might just get a number out, in which case that's a horizontal asymptote. We're going to get that number out when the degree is the same in both of them. That's when I say a number, I should specify that's a non-zero number. We might also get 0 out, but we're only going to get 0 if the degree of the denominator is larger than the degree of the numerator, because we're going to have an x left over, or maybe perhaps x raised to a power even, left over in the denominator. So that expression is going to get super, super small as x gets super, super big. Or if the degree of the numerator is larger than the degree of the denominator, then our y values are going to end up going towards either infinity or negative infinity. We just need to be careful about which it is. If we have an odd power left over, then as x goes to infinity, y will go to infinity. As x goes to negative, y will go to negative. If we have an even power left over, then they're both going to end up going to positive. Now this is, of course, I should even clarify that. Hey, if I threw a negative 3 out there, then that's going to change the sign there. And then that's going to end up changing the signs on both of those. And same thing down here. So really the key there is to just consider what the coefficients are of your highest degree terms. Check their sign, and then check your power on the x that's left over. And then just consider whether you're doing x to positive infinity or x to negative infinity. Best not to take too many shortcuts on that one. Really make sure that you have all the pieces set in place. If you'd like to see this in all of its algebraic glory, here it is. I understand that for some of you this might seem like it's just a little too much, but I think this is very nice. So this technique we're discussing right here, it works for any function that's in this format, where the numerator and the denominator are both polynomials. They're just a whole bunch of terms being added or subtracted together that are x's raised to powers and perhaps multiplied by a coefficient. This is a subscript, so we pronounce this a sub n. That's the coefficient for x to the power of n. A sub n minus 1 is the coefficient of x to the power of a minus 1. A sub n minus 2 is the coefficient of x to the power of n minus 2. Plus dot dot dot, so I'm skipping a bunch of terms here. And then I have a sub 2 is the coefficient for x squared. A sub 1 is the coefficient of x to the first. And then I'll end with a sub 0, which is the coefficient of x to the 0, but we know that if it's x raised to the power of 0, that's just going to be 1, so we can ignore that. And then same thing down in the denominator, I'm using b's and m's. So as I consider what happens when x goes to plus or minus infinity, my function kind of gets simplified down to just being the leading terms. So the terms in the numerator and the denominator with the highest degree. That's what we got there. And then, if it turns out that those exponents are the same, if n is equal to m, then our y value is going to settle in on the horizontal asymptote, which is just the coefficients of my leading terms. If n is less than m, so the denominator has a higher degree than the numerator, then y is going to go to 0. And if n is greater than m, then y is going to be either plus or minus infinity. You definitely need to check to see whether you have an even or an odd power left over when you combine your terms in the numerator and the denominator by subtracting exponents. If this algebraic rule seems like way too much for you, just think about it in terms of the general rules we discussed on the previous page. We can also extend this idea to things like square roots. In this example, again, I do not care about that 100 because it will be super small in comparison to my x squared term. So now my function is 12x over the square root of 16x squared, which, you know what, I'm going to rewrite that as the square root of 16 multiplied by the square root of x squared. The square root of 16 we know is 4. That's great. What is the square root of x squared? If you said x, that's almost correct. It's the absolute value of x. You may recall this as one of the algebraic rules for the absolute value of x. It is the square root of x squared. We can now simplify this to be 3x over the absolute value of x. So now when x goes to positive infinity, well, if x is positive, then the absolute value of x is just x, which means this is going to simplify to 3. I will have a horizontal asymptote of 3 as x approaches positive infinity. As x approaches negative infinity, I now have a negative x value, and the absolute value of a negative number we know is the opposite of that number. Therefore, this is going to simplify to negative 3. So it's horizontal. This is an example of a function with two horizontal asymptotes, one at negative 3 and one at positive 3. If you didn't like all that with the absolute values, then just focus in here. When we put a positive number in for x, we're squaring it, which is going to give us a positive number times 16 square root. It's all going to be a positive number in the denominator, and then also a positive number in the numerator, since it's 12 times a positive number. Positive divided by a positive is a positive, and that's the sign that we had there. If we put in a negative value for x, we're still squaring it, which is going to make it positive. Positive times a positive is positive. Square root of that, it's positive. But the numerator is still going to be a negative times 12. Negative divided by a positive is negative. That's a sign that we had there. So as far as end behavior is concerned, we should be able to look at a graph and identify what the end behavior is. We should be able to state whether y is approaching positive or negative infinity or approaching a horizontal asymptote. If we're given a graph, there will be no tricks. It will be obvious from looking at it. As far as dealing with what the equations are, we're just using these shortcuts. It's always going to be something with x's and powers. And we're just considering where is the power bigger. Is it in the numerator? Is it in the denominator? Is it the same in both? Later on in the course, we're going to study other special types of functions where we're going to have to think about them differently. But those techniques will be very specific to those function types. So when we see exponential functions, we're going to know they have a horizontal asymptote, and then one end goes to either plus or minus infinity, and that'll be a guarantee. And then we can use techniques specific to exponentials for that. When we study trig functions, we're going to know that they're going to exhibit periodic behavior, and we're going to have special techniques to discuss what type that is. But for most of the functions that we look at, we're going to use the techniques that we discussed here. Discontinuities, we got two different types of those. They've each got two different names. Again, we should be able to identify them from a graph as well as from looking at an equation. So take a deep breath. Think back about everything we've talked about so far. So now when we're given a function, just the equation, there's so much that we can work out about that function now that we might not have been able to do a couple weeks ago. We can identify what the domain of that function is, so all the possible x values that it exists for. We can identify the areas, the intervals where that function is positive and where it is negative. We can identify any discontinuities that it might have and classify those discontinuities. We can also identify what its end behavior is. Is the function going to go towards infinity or negative infinity, or is it going to settle onto a horizontal asymptote? With the help of technology, we can also identify where functions are increasing or decreasing and where their maxima and minima are. Later on, once we know some calculus, we can do that by hand as well, but that'll take some time for us to get there.